Good morning and welcome to our today's seminar, Anchoring in Concrete Using Quick Anchor version 3. I am Pro Dasgupta and I have been involved with the development of this program from the very first day of its inception. We have a large crowd today and I am very excited to be here and I thank you for being here with us today. This is a short 1-hour presentation, so at times I may have to go a little fast, but we are recording the seminar and hopefully the recording will come out nice and we will be able to share it on YouTube, so for you to refer back to it in the future if you need to. Just wanted to mention, and you know this already, but this seminar is really not on Appendix D of ACI 318. Of course, Appendix D will always be there in the background, but the seminar is really on how to use Quick Anchor and the inner workings of the program. And we will also have a Q&A session at the very end. You can type in your questions at any time in the Q&A box. Don't know if I can point to the box, so probably not. Anyway, the box is right next to the slide, and but I'll then respond to those questions at the end of my presentation, and I'll try to cover as many questions as possible without going over time by too much. Now, before I begin, I would like to run a short poll and to see exactly where we are as far as what kind of experience you have using Quick Anchor and which version of Quick Anchor you're using right now, or if you're using Quick Anchor at all. I mean, some of you may not be using it and may plan to buy it. So let me open up this poll. I'll probably spend about half a minute on this. So if you could click on the options that applies to you, that would give me a good idea. I think I'll give it about 10 more seconds. Oh, all right. So it looks like most of you have not actually used Quick Anchor yet, which is good. That this seminar will give you a good idea about how the program works and how useful it is, and if it is good for you. And I can also see that people who are actually using it are using version 3, which is also good. It's always good to keep the program up to date, so that all the kinks, when all the kinks have been ironed out, all the new features are included, etc. All right, so I think I'll stop the poll now. And so what I will do, I will start by launching the program on my screen and go over the program interface and point out a few things that you might find useful and interesting. So I will, and then I will switch gear and discuss some of the inner workings of the program that would help you to use the program more effectively and interpret the outputs more easily. So just stay with me for a few seconds when I switch the screen, and I'll start to share my desktop, which will happen. All right. I think it takes a few seconds for your screens to update. So, and okay, so I think by now you can see my desktop. So I'm going to launch the program. The current version is 3.3.1. You can check it by going to Help and then click About. So you can see here the version is 3.3.1. If you're already using Quick Anchor 3 and your version is anything lower than that, you may want to just update it. It's just easy. On your interface around here, you will see a message pop up if your program is actually lower than the current version, that there is an update available. So you just click on that link, that would download the updated version on your computer, and just install it on top of your current installation, and you're good to go. Now, so this is the program interface, and people who are using Quick Anchor version 3 are familiar with it. People who are using a lower version will also find many things similar to the versions they are using, but many things are also different. One thing that is different from any older version is this these two options that we have now for anchor arrangement. In the older versions, what we used to have is what we call now a grid type arrangement, where, for instance, if you look at this picture, we have a 4x3 or 3x4 arrangement where all the anchors in the grid are present. But now we also have what we call a perimeter arrangement, where the middle anchors that were here they are now removed. So this is helpful if you have a base plate where in the middle you have a member attached to the base plate, and then the anchors are arranged around the perimeter of the plate. And so this is new in version 3. And you would also notice that we have now added the base plate itself. The program does not actually design the base plate, but the only reason the base plate has been added is to take a bending moment and calculate tension and compression in the anchors. So the base plate section is used as a beam section, and you can have bending moment about x-axis and bending moment about y-axis. So we do a regular beam type analysis with biaxial moment to see which anchors are in tension and which anchors are in compression. And for tension analysis using Appendix D, the anchors that are in tension, only those anchors are included in the analysis using Appendix D provision. Now, this is also another new feature in version 3. In the lower versions, you had to do this job yourself and input only those anchors that are in tension. But in version 3, you don't have to do that anymore. You just input your whole anchor arrangement, and then you will input all the loads, and I will go over that, the load input part, very shortly. And the program does the rest. So it will analyze the anchors for the imposed tension, imposed moments, imposed shear, torsion, etc., and see which anchors are resisting tension, which anchors are resisting shear, and include those anchors only for Appendix D to apply Appendix D provisions. And that is what is required by Appendix D. You do not consider anchors that are in compression for into the group that you include in the Appendix D calculations. So this base plate is really required for that beam type flexure analysis, biaxial flexure analysis. And so if you do not have a bending moment, and when I say bending moment, it could be a directly applied bending moment about x-axis or y-axis. or it could be a tension with an eccentricity, which would also cause a bending moment, and a net bending moment about the centroid of the anchors. So if you do not have any of those, then you could very safely uncheck this box at the bottom of the screen next to the text base plate, and you will see this message pop up that the base plate will be required if there is a bending moment or eccentrically applied axial load acting on the anchors. But if you don't have any of those, switch it off. Base plate is not necessary at all, and the base plate also goes away from this figure. But for now, I would like to switch the base plate back on just to show you a couple of things. So when you start, you already know this, when you start inputting the anchor arrangement first, this first tab of this interface is mostly for anchor arrangement and the type of anchors you are using and its sizes. So let's say we have a perimeter arrangement, and we have 8 anchors arranged, and then let's have them arranged in 3 rows, and with 8 anchors, automatically the number of columns will be filled in as 3 because the middle one is not there. And then you enter the edge distances of the anchor. By the way, the gray area behind this base plate, it shows the extent of concrete. So the edges of the gray area are the edges of the concrete, on where the anchor is installed. So C sub L is the left edge distance of the anchor arrangement. This is very important to note, that this line right below the picture is about the anchor dimensions, the dimensions of the anchor arrangement, not of the base plate. And I realize that there is probably a lag between when I'm showing something and when that actually happens on your screen, so I'll try to speak slowly so that you can understand where I'm pointing at. So so the first box, C sub L, is the left edge distance of the anchor arrangement, and so let's just say it's 5. So that, and once you click on any other box, the picture gets updated and it now shows 5. The next one is S sub X, which is the spacing between the anchors, between the anchor columns. And by anchor columns, I mean these lines of anchors that appear vertical on the screen, on your screen, and then we have anchor rows that are horizontally oriented. And so S sub X, just put 5, let's say, and C sub R. So C is edge distance as per Appendix D, and S is the anchor spacing, and C sub R is, let's say, it is also 5. And then C sub T, which is spacing edge distance from the top edge. So let's say that is 8. S sub Y, which is the anchor spacing along the y-axis. So let's say that is also 5. And edge distance towards the bottom edge, let's say that is 6. And once you click somewhere else, the whole figure is revised to reflect all these changes that we have made in the input. Now you might have noticed already that while we were entering those values of anchor arrangement, the base plate numbers, the first 2 numbers, L sub px and L sub py, are the base plate dimensions along x and y axis. So this is your, from here to here is your L sub px of the base plate, and from here to here is your L sub py for the base plate. I'm sorry. So, and these numbers, and also the base plate edge distances, the C sub PL, C sub PR, now these are the edge distances of the base plate as opposed to edge distances from the anchors. And these numbers are updated based on some built-in assumptions in the program, how big the base plate is compared to the anchor arrangement. But of course you can change them if you want. But these are just the preliminary values just to update the figures. But if you want to change them, you can always do that. But just make sure that the, let's say, base plate, what you put as the length of the base plate and what you put as the edge distances, they kind of match with what you have with the anchor arrangement. Like in total, the sum of the base plate length, the base plate right edge distance, and base plate left edge distance should be equal to the length of the concrete that you can calculate from the anchor arrangement from above. So for now, I'm not going to bother with changing the base plate dimensions or spacings. But as I said, if you do not need the base plate, like if you do not have any moments or anything, then you can simply switch it off, and that would be it. And then you need to select what type of anchors you're using. So you could use headed bolt, headed stud, hooked bolts, and then so these first three options are, of course, cast in place anchors, and then the last three options are post installed. Adhesive anchors has been added new. I think those of you who are using version 2, you have it too. So it was added in Appendix D in ACI 3.18.11 edition. So, and Quick Anchor incorporates that. So you have adhesive, undercut, and expansion. So you select your type of anchor. It could be headed, let's say it is headed bolt. Then you enter the anchor diameter, which is effective in resisting tension. And that is basically the nominal diameter minus the area taken up by the thread. You need to deduct that amount to get the solid area, cross-sectional area of the solid shank of the anchor. So one way, and you can always type those values in if you know your values. The anchor diameter, well, this is the nominal diameter, and here you enter the effective cross-section area where you deduct the thread. And here, if it is a headed anchor, that is, if it is a headed bolt or headed stud, then you enter the head area A sub B or G, which is basically the total area of the head minus the anchor cross section. And in this case, you actually do include the threads. When you deduct the cross section of the anchor from the total area cross section of the head, you do include the thread, because so that you know exactly the area of the head that is actually bearing on the concrete. Now, if you don't know your value, all you have is just an anchor diameter that you're using, then you can always click on this help button, and here you can select from 1/4 of an inch to up to 4-inch diameter anchor. And let's select 1 inch, and you can leave it as coarse thread or fine thread if you know, and then and you can select what type of head your anchor has. It could be a hex head, it could be heavy hex, it could be square, and the program calculates all the necessary quantities, and then you click OK, and all the quantities are brought into these boxes, and then you enter the effective embedment depth of the anchor. So let's say that is 6 inches, and then the depth of concrete itself, which obviously cannot be less than 6. So let's just say it is 10 inches. And eccentricities, that is the eccentricity values in the x and y direction are basically where the connected member is located with respect to the anchor arrangement. So these eccentricities are with respect to the centroid of the anchors. So if we, and so positive value is will move the member, attached member, in the positive x direction. So if I put 1, you can see this member basically signifies this eccentricity, the location of this member. And if you put -1, and then it moves to the other direction. So for now, let's just keep it at 0. So then we go to the next tab of the program, material and reinforcement. This is very straightforward. You just type in your concrete strength. The strain values of the concrete you don't have to mess with unless you really want to. And anchor steel, you can select from a number of different grades of steel, or the particular steel in the anchor grade that steel you're using is not included here. You can always select other, and then you can type in the appropriate values. This is the ultimate strength, tensile strength. This is the yield strength, and this thing shows you if the steel is considered ductile or not. What is a ductile? That definition is included in Appendix D. What steel we consider as ductile. All the other steel that are included in all the grades that are included here, they are all considered ductile. So those boxes do not appear here. Then we have these two items under shear loading that are really relevant for shear analysis of anchors, and that too if you have anchors continuously welded to the steel attachment. So for instance, if we had a welded stud, and of course welded stud cannot be used without a base plate, and okay, let's bring back our anchor diameter, and then you go here, you'll see you can select this box, of course, and then there is another provision that you can check in Appendix D, section 6.2.3. So if you meet this second condition, then you could achieve a slightly higher shear breakout strength of the anchors, and although it's not necessarily it will be higher, but there is an equation that gives you a little higher value in shear breakout, and the first option also works with that, and to give you, if you do qualify for both of these, then you do get that a little advantage you might get. Supplementary reinforcement to enhance the strength of anchor concrete breakout under tension or shear. In tension, Appendix D just tells you that if either you have it or you don't have it. No other options. So if you have it, then click yes. If you don't have it, leave it at no. If you have it, then your strength in concrete breakout goes up a little bit. In shear, we have three options. Option 1 is basically you don't have it or have a minimal amount. Then you don't get any advantage, any benefit of selecting option 1. And which option is what is you can kind of see from this tooltip. This tooltip is there for all the input boxes on this program interface. So you could select option 1, option 2, option 3. Option 3 is the highest one where you get the highest enhancement in your strength. But of course, you have to provide reinforcements, supplementary reinforcement in a certain manner to qualify for this. But that is about Appendix D, not about the program itself. And then you have anchor reinforcement, where if you want to suppress concrete breakout altogether, and then let the reinforcements take up all the shear forces or tension forces instead of relying on the concrete. So then you can provide anchor reinforcement. Then you calculate. You can provide an anchor reinforcement for tension as well as for shear, and in both cases you just enter the design strength of the anchor reinforcement in that particular mode of failure directly, and then the program then does not bother to check with anchor breakout in concrete breakout under tension or shear, whichever direction you provided the anchor reinforcement for. Then you go to load. Again, very straightforward. First, we get the loads that contribute to the tension in anchors. Of course, the first one is the direct tension that is being applied, and then you have bending moments. So I'll just put tension of 10 and bending moment of, this is about x-axis and this is about y-axis, m sub uy. And you can also see that the positive moment causes compression at the top edge of the plate. That is for when the moment is about x-axis. And for moment about y-axis, the positive moment causes compression at the right edge of the plate. So you can enter plus or minus depending on the direction of your moment. Now, if you have seismic loading, the direction of your moment will obviously be reversible because seismic load is reversible. So the program will consider only the direction that you enter here. So you will need to, many times it will be clear which direction is critical, so that's the one you will enter. But if it is not that clear, then you may have to, well, you will have to enter, run multiple analysis with different directions. For tension, you can typically you don't, if you just have compression, not tension, then you don't need to enter compression. You can just leave it as 0, except when the compression is accompanied by moments. Then you better include the compression as well, because that will alter the force arrangement caused by the moment. And then we have these boxes that say seismic percentage. Now this is only relevant if you are using ACI 31811, as most of you are probably doing anyways. And ACI 318 Appendix D has certain special requirements that apply only when you have seismic loading on the anchors. Now in ACI 31805 and 31808, those requirements kicked in if the seismic design category of your building was C or higher. That was the only criteria. But now, starting with ACI 31811 and also in ACI 31814, we have a separate for these seismic requirements to kick in. You not only have to have seismic design category C or higher, but you also need to have the loading on the at least 20% of the total loading on the anchors coming from seismic forces. So in other words, even if you have a building in SDC C, but the loading on the anchor, only 5% of the total load on the anchors is coming from seismic, then you do not need to use the special seismic requirements of the code, which is good because those requirements could be pretty onerous. So let's say in our case, let's just put 100% of the tension, 100% of the moments are from seismic loading. So this is a seismic percentage. The percentage of the total anchor force, total tension, total M sub ux, and total M sub uy that are coming from seismic loading as opposed to other loadings. And then we have these little box that talks about sustained loads, and this applies only for adhesive anchors. And you could see that these boxes are now actually not active because the anchor I have selected is not adhesive. So, but if you have an adhesive anchor, then you need to also type in the part of the tension and the moments that are sustained in nature, basically from gravity load. For instance, if you are designing an anchoring a light fixture, anchoring an overhead anchor on the ceiling to hang a light fixture, then the tension caused by the gravity load from the light fixture is a sustained tension on the anchor. And if the anchors are adhesive anchors, then you need to include that portion as the sustained tension in this box, because ACI 318 does have special requirements for sustained loading, that we need to check the sustained loading under a lower level of strength. But of course, this sustained loading is basically a part of the total load that you have already included here. And then we have shear forces, shear to the right in the x direction, in the y direction, and then we have torsion, which will also cause shear in the anchors. And as usual, we have the seismic percentages of all those loads. And then we have these post-install anchors, where, I mean, all these boxes are now deactivated because the anchor I have selected is not post-installed, it's a custom place. But if, let's say, if I go back and select a post-install anchor, and again, I just select some diameter, doesn't matter what. So you can see you have to select what category it is in. And then these are the boxes that these input parameters you should typically get from the ICCES reports that the manufacturers of your post-install anchors will share on their website. So if you are using a particular type of anchor, you download the corresponding ICCES reports, and those reports will have tables that will give you all those values that are required by the code to calculate the strength of the post-install anchors. If you do not by any chance have those values, the code does have equations to calculate them, some default values. So if you do not enter anything, if you have a post-install anchor and do not enter anything in these boxes, then the program will just use the default values provided by the code. But please know that those default values are really, really very conservative compared to the values you will get from the manufacturer's test reports. And now, to get the values out of the manufacturer's test reports and entering it here, I understand this is not all that user friendly compared to, let's say if you're using the Hilti's Profis, and there you could just select one of their anchor products, and all these values would be brought into the program automatically. But the good part of Quick Anchor is that in this way you can actually compare two similar anchors from two different vendors and see side by side exactly how they perform under the on the same program. And then you have just miscellaneous. These are all very self-explanatory. If you know Appendix D, then none of this should be a problem. And then you could just run the program. It runs, and this already. You have a simple output that just gives you the final strength, the final results in short. And then you can also click on the detailed output that gives you the step-by-step calculations, starting with all the input parameters that you have already entered, and then you can go through the pages to see all the step-by-step calculations as required by the ACI provisions. So from here, I think I'm running out of time. So from here, I will switch gear and open this slide set to talk a little bit about what happens once you click that run button on the program. So what is going on? So the first thing that happens is that the program takes all your input loads and calculates the loads on the anchors. So for instance, let's work with this arrangement. We have, this is the concrete, and now I can use my pointer. Okay, so this is the concrete base, let's say, and we are anchoring a base plate. This is my base plate, and anchored by these 8 anchors. So, and then we have these 2 moments acting on these anchors, m sub x, m sub y. So what the program will do, will calculate under these 2 moments which anchors which anchors are under tension, caused by these 2 moments. If there was a direct tension, that would be included in the analysis too. And this is done, as I mentioned before, by using a biaxial flexion analysis, with the base plate as the section and the anchors as if the anchors are the reinforcements in a beam, and the base plate is the beam section. So here you can see that, let's say, the 3 corner anchors are in tension, and these other 5 other anchors, they are in compression. So when you are using the tension provisions of Appendix D, then we only consider these 3 anchors, not these other anchors. But these are the 3 anchors marked by this red color. They are the tension anchors, and only those anchors will be used for tension analysis. Now let's say at the same time we have, on top of the tension, we have a direct shear acting as V prime u sub x in the x direction, as well as a torsion m prime u sub z. The only reason I'm using the prime, because these forces are actually not used as far as Appendix D is concerned. When we use Appendix D, we use the forces that we get from resolving these imposed forces. So that creates this kind of shear arrangement in all these anchors. Many of the anchors are carrying shear in x direction, and in x, positive x, negative x, and these anchors are also carrying shear in towards the upward and then downward shear. So what we do, so what quick anchor does, it would consider first in the x shear, for shear in x direction, it would consider these 2 lines of anchors, these 2 rows of anchors, where the shear is acting in the x direction, and we know all those values, the individual values of those anchor shears, and then we can calculate a net shear that is acting on these 5 anchors, and then it would also calculate the net shear and its strength on these 3 anchors that are in the opposite direction, and see which one is governing, which one has the lower strength, which one has the more chance of failure. Is it going to fail in this direction, in the positive x direction, under these loads, or is it going to fail under the negative x direction, under these loads? Of course, in this case, it is very clear that it's going to fail in the positive x direction under these loads. Same with the y direction. Even though it did not have a direct shear force in the y direction, but due to the torsion, we still have now a net shear in y direction. In this line of anchors, we have an upward shear in the y direction. In this line of anchors, we have a downward shear in y direction. See, at the end, we resolve the imposed shear forces and torsion into these 2 subgroups of anchor. This group of 5 anchors is carrying shear in the positive x direction, and this group of this one line of anchors is carrying shear in the negative direction of in the negative y direction. And we have determined that this is the one that is governing, this is the group that is governing in the x direction. The program determines that. And this is the group that is governing for shear in y direction. And now these are the two groups that will be considered for shear analysis. So you can see that even though we have a same set of anchors, the tension analysis is being carried out on these three anchors, and the shear analysis are carried out for x shear, these 5 anchors, and for y shear, these 3 anchors. So it could always happen that different subgroups of anchors are being used for tension or for shear analysis, which is completely fine, and that is what Appendix D requires us to do. So the first mode of failure under tension is still failure. It's very simple. We have these 3 anchors in tension, and obviously the corner anchor will have the highest tension force, as well as it is closest to the 2 edges. So this is the one that well the edges, it doesn't really matter in this case for shear for tension failure of steel anchors, but it does have the highest tension. So this is the one will be governing. So we will calculate the strength of this anchor and compare it with the tension that we have calculated acting on that. Concrete breakout under tension. Now ACI 318 requires us to consider a breakout surface like this that has an extent of 1.5 times the H sub EF, which is the embedment depth of the anchor, on all sides of the anchor. Now this is only for one anchor. Each anchor will have its own breakout surface like this. So in our case, the anchors could have breakout surfaces like this. Of course, the part that is falling outside the concrete, we neglect that part. We exclude them. But inside, individual breakout surfaces could overlap. Then this is the net breakout surface that we use for concrete breakout analysis under tension. But under a different scenario, if the embedment depths were shallower, then you could also have a scenario case like this where they're overlapping only in one direction and not in the other direction. They're overlapping in this direction but not in this direction. Then these anchors are not in a group. So we have 2 separate groups of anchor. The first group is this one. This is just one anchor, a group all by itself, and then and the second group is made up by these 2 anchors because their individual failure surfaces are overlapping. And in the program we call them column 1 and column 2. It's counted from the left hand side. So we calculate the strength for each column, strength in concrete breakout in tension for each column separately, and compare those strengths with the respective tension forces that are acting on those columns. So for instance, for column 1, the strength would be compared against the tension that is acting on this one anchor only. For column 2, the strength would be compared against the net tension coming out of the tension on this anchor and tension in this anchor. And whichever one governs will give us the net tension breakout strength. And you could also have a situation where they are not overlapping at all in any direction. Then all of them are basically individual, will undergo individual failures. And then again, this will definitely be the governing anchor because it has the highest amount of tension, and also it is very close to the 2 edges. And you know that the edge distance is important for concrete breakout. Pull out is probably the simplest one. Again, it's the individual kind of failure. There is no group action here, so the governing anchor is this one. Side face blowout. There is not much complication except that we have these three anchors that are in tension. Now, the top two anchors could try to break out along this top edge and this side face, or the side face blowout could also happen from these two anchors trying to break out sideways in this direction. So we check both of these and see which one is governing. Of course, actually, I mean, in general, the program checks in all four directions, but of course, in this particular case, the direction in this direction and this direction, they're not going to govern anyways. But program checks it anyway, in any case, and see which one is governing. So that brings us to concrete breakout, and I guess I will have to speed things up a little bit. So concrete breakout is, if you look at Appendix D in ACI 318, concrete breakout is actually the second mode of failure in shear. We are now in shear loading now. So you can see D6.2 gives us concrete breakout. D6.1 gives us steel failure under shear. But I will discuss the steel failure after I have discussed the concrete breakout, and you will know why when I do that, when I discuss the steel failure. So let's start with concrete breakout under shear. And just like concrete breakout in tension, ACI 318 requires us to consider a breakout surface like this. This is the plan view, and a 35-degree angle starting from the anchor, but this is only for one anchor. And on top of that, ACI 318 also requires us to consider a number of cases. So in the first scenario, we have S that is greater or equal to C sub A11. Now S is anchor spacing, and in this context, S is the anchor spacing in the direction of the applied shear. So this picture is from ACI 318.11, and S is the distance between this anchor and this anchor in this direction. And C sub A1, 1 is the edge distance of the first line of anchor from the relevant edge. Now, if the anchor spacing in the direction of shear is more than the edge distance, then the ACI 318 requires us to consider these two cases. Case 1 is where the total shear is being resisted by both of these anchors. They're only showing two anchors, so basically what it means is that all anchors are sharing the shear load. And then there's the case 2 where we assume that the first line of anchor has failed, and by failing it, what we really mean is that some cracks have developed, so it became less rigid compared to the back row, which has not failed yet. So all the loads, total shear load, will move to the back row only. So this is another mode of failure starting from the back row, where the total load is acting on the back row itself. This is case 2. And then there is another scenario where this spacing S is less than the edge distance. Then you only need to consider one case, which they call case 3 in Appendix D, where the total load is applied on the front row only. That's it. On top of that, ACI also requires us to consider a failure mode where the failure actually takes place parallel to the application of the shear. In these modes, the failure is taking place perpendicular to the application along an edge which is perpendicular to the direction of the applied shear. But now we're talking about failure taking place along an edge which is parallel to the applied shear, and ACI requires us to consider that as well. But it doesn't really tell us exactly how to reconcile this parallel failure with all these cases that they've given us for perpendicular failure. So we had a lot of discussion internally within our company. We have talked to people that are knowledgeable about these issues, and I have also consulted the European code, the anchor provisions in the European code, and the provisions in the European code are very similar to the Appendix D because both sets of provisions are basically based on the same research, except that their provisions are a lot more complex, actually, if you can believe it. So based on all that, so this is what we have come up with, and this is what Quick Anchor does. So to begin with, let's say the spacing of the anchors in the direction of the shear is S, that is more than C sub A11, which is this. Then the case 1 would be this, where all anchors are sharing the imposed shear. And when I say all, I really mean all anchors that we have already identified as the ones that are carrying shear in the direction that are governing. In this case, these 5 anchors. If you remember that these 3 anchors are carrying shear in the opposite direction from the load analysis of the shear load, and so you're not considering that. So when I say all, I really mean all of these relevant anchors. They are carrying the shear, and the failure is taking place from the first line of anchors, like this, as shown here. So and we calculate, using Appendix D, we calculate the strength of this kind of failure, and we compare the strength against an imposed shear of V sub ux1 plus V sub ux2. These are the shears acting on these 2 anchors only. Because that is the load under which the failure is, this failure is taking place. And then for the same load arrangement, we consider, so this is basic, so this arrangement, so this loading arrangement is basically the same as this case 1 as in Appendix D. And then we consider failure parallel to the applied load for the same load arrangement where all these relevant anchors are carrying shear, but the failure is not taking place parallel along the edge, which is parallel to these anchors and closest to an anchor line. In this case, this is the failure that you are looking at, and Appendix D tells you how to calculate the strength of this parallel failure, if you will, and compare the strength against this total imposed load, V sub ux1 plus V sub ux3 plus V sub ux4, because these are the loads that are causing this failure, loads only on these 3 anchors. And then we go to the next step, where we assume that the first line of anchors have failed and all the shear has moved to the back to 2 lines behind the first line that has failed. So these are the 3 anchors that are now active, and we need to recalculate the loads on these 3 anchors. For instance, this V sub ux3 shown here is not the same as V sub ux3 shown here, because when we come here, we start from the imposed loading, that the imposed shear and the imposed torsion, and recalculate the individual anchor shears with the assumption that the first line is now gone. So you only have these many anchors and how the shear would be distributed. So based on that. So, and then in this case, we just have 1 anchor in the second line, and the failure is taking place from the second line, which is the perpendicular failure, and this strength is checked against V sub ux3. And then again, for the same loading arrangement, we consider the parallel failure like this. And then we go to the next step, where even the second line also has failed. So all the load has gone to the farthest row from the governing edge. The governing edge is obviously this, and the furthest row is this one. The first two lines, the furthest line, the first two lines have failed, so only the last line remains. And so now we have two anchors here. We recalculate the forces in those two anchors, and then this is the failure surface. They are overlapping, of course, and this strength is checked against vis-a-vis x4 plus vis-a-vis x5, which is basically the total shear that is acting on the anchors. And as usual, we again consider the parallel failure condition. So that takes care of shear in x direction, and the governing shear strength will come from all these 6 analyses. And so, and then we also have, and then let's talk about the scenario where we have the spacing less than the edge distance. Then we only have just one case where the total shear is acting on the front row only. So in this case, so that gives rise to basically 2 cases as far as quick anchor is concerned, because one is failure perpendicular to an edge, and the other is the failure parallel to an edge, but the rest is still the same. And here in this case, the governing failure is determined based on just these 2 analyses. One is this, the other one is this. And I think I'm out of time, so we'll probably have to go beyond time a little bit, but I'm trying to finish it up very quickly. And that brings us to steel failure in anchor. The reason I left it for after the concrete breakout is because in ACI 31811, they have included a new provision, and which continues in ACI 31814, that says where concrete breakout is a potential failure mode, the required steel shear strength shall be consistent with the assumed breakout surface. This provision was not there in 1305 or 08, so this is not applied in your by quick anchor if your governing code is 1305 or 1308. But if you are using 1311 and in future 1314, what would happen as required by this provision is that the program first determines what is the governing failure mode in concrete breakout, and what are the anchors that are actually resisting shear in that failure mode. So let's say if this loading arrangement that we called case 1 before gives you the governing failure mode in concrete breakout, where all the relevant anchors are resisting shear and the failure is taking place from the front anchors, then you can see that 5 anchors are resisting shear. So we consider all of them, and we consider this load distribution to calculate, to see that which of these anchors are has the highest amount of shear in it, and we calculate the shear strength based on that and that loading. On the other hand, if your governing failure mode in concrete breakout is this, where the first line of anchors have failed already and all the loads have moved to the back 2 lines, then we only consider only these 3 anchors for shear in steel strength of anchor in shear determination, and obviously this case is more onerous than this case, because here we have more number of anchors resisting shear, so they're sharing the shear, so the shear acting on an individual anchor would be lower compared to shear acting on an individual anchor in this scenario. So this is a kind of an onerous requirement that is part of ACI 1311 and 1314, and quick anchor also applies that requirement only when those two codes are selected. Well, 31814 is still not part of quick anchor, but it will be in the future. But if you are using 31805 or 31808, then we just, no matter what the governing mode of failure was for in concrete breakout, it will the steel strength will always be determined based on this arrangement. And that brings us to the last mode of failure, concrete pry-out. There is not much to say about it, except that the concrete pry-out strength is determined based on the nominal concrete breakout strength in tension. So this is basically an empirical way of calculating the pry-out strength in shear based on a concrete breakout strength in tension. Now, one thing you need to take note is that the nominal concrete breakout strength in tension is not the same as what we determined in our tension analysis based on these three anchors that are actually carrying a resisting tension. No. The nominal shear strength, concrete breakout strength in tension for pry-out purposes will need to be calculated based on these 5 anchors that are being considered for shear analysis. So we need to rerun the concrete breakout analysis in tension based on these 5 anchors and use that value for pry-out calculation. So do not try to compare your pry-out strength to your strength calculated in the tension area of the output because they may not match, because the basis of calculating those two values could be completely different. And the last item, very quickly, is the interaction. This is the interaction equations that ACI gives us. This equation is a curvilinear equation, a continuous curve running from here to here, and this one is just a simplified version, a trilinear simplified version of this. But this is really the one that has been developed from the research that formed the basis of this whole anchor provisions. And just the reason is the Appendix D does not give us a way to incorporate biaxial shear. You can see the equation has only one quantity for shear, but what do you do if you have shear in both directions acting at the same time? You need to calculate the shear strength in x and y directions separately, because Appendix D does not give you any way of calculating shear in an inclined direction. So it has to be, you need to calculate the shear strength in concrete, let's say in concrete breakout, in x direction and in y direction separately. But then how do you combine them in the interaction? So we did had a lot of discussion internally with the people from outside, and what really came out was, and we thought we kind of came up with this interaction equation that includes biaxial shear in this manner. Basically, we just threw in this one additional term with the same exponent. So essentially what we are doing is that we are taking this planar curve and making it a 3-dimensional surface, and so from an interaction curve it becomes an interaction surface, and our whatever loads and strengths that we have on our anchors needs to be within this surface defined by this equation. So that's all I had for the quick anchor discussion. So let's see what questions do we have. Okay, the first question is, when you enter a moment into the program and define your base plate, how does the program determine the compression block to be able to determine the moment arm, etc., of the anchors? Yeah, so as I said before, it is done following the regular beam analysis by using Whitney's stress block. Actually, no, we do not use Whitney's stress block. We actually do use we slice the whole section. We consider this base plate as a beam section and the anchors as the reinforcements, and then we divide the whole beam section, if you will, into a number of layers, and then we do run a numeric analysis just like you would do for a beam. And we use a concrete stress strain curve and a steel stress strain curve that are built into the program, and then calculate which anchors are in tension and which part of the, let's say, which part of the beam is in compression. And this is actually a biaxial analysis, so it's not so that you can have two moments at the same time. So, and this is now, of course, this is not really an exact way of doing things to determine how the forces are distributed into different anchors, because this is really not a beam. Basically, the plane section remaining plane, that assumption is not exactly true for a base plate with anchors, but for most practical purposes it works fine, and I believe that most other programs also do the same thing. Let me see. Well, the next question is using leveling nuts under base plate. Well, I don't know why that should be. I mean, of course, there is no way to enter the leveling nut in the program, but I mean, in the program, we just have to assume the base plate is level. And I mean, I tend to, I mean, to be conservative, I would just assume that the lowest point of the concrete, I mean, just take the embedment depth of the anchor from the lowest point of the concrete, of the concrete, the concrete surface. How can I input a circular plate and a circular bolt layout? As of now, you cannot. This is something on our radar, and we might include this in the future if we think that there is a demand for that. Is it possible for us to have a copy of this presentation? As I mentioned, I do not believe we will gain much by having a copy of this the PowerPoint presentation I showed. But as I said, we are recording this seminar, so we will make the recording available on our YouTube channel. If you don't know how to access that, go to our website. From there, you will see a link on our homepage. You will see a link to our YouTube channel, and you will see very soon, I'm sure, maybe not today, but in the next few days, this whole recording should be available on our YouTube channel. Till what point would you consider the concrete area infinite for edge distance? Well, the point beyond which any of well, if you're just considering tension, then it really depends on if the edges are beyond your tension breakout failure surfaces, tension breakout surfaces. So if you look at Appendix D, the tension breakout surface goes from the center of the anchor to 1.5 times the embedment depth of the anchor in all directions. So if you have an edge that is within that 1.5 H sub F distance, then that edge will cut off the it won't allow for the whole concrete breakout surface to develop, so that will reduce the strength. But if your edge is beyond that point, then it doesn't really matter how far it is from. So it could be 1 inch bigger, it could be 10 inch bigger than that maximum extent where that is required for the complete development of the concrete breakout. For shear, if you are considering the edge distance for shear breakout, I do not know there is anything that you can call infinite. Of course, there is something beyond which the strengths will level off. I think in the European code, if the distance is more than 10 times the anchor spacing or something like that, I don't remember exactly, then you don't have to consider concrete breakout in shear. They call it edge failure. But Appendix D doesn't have anything, so in theory there is an infinite. But if it is very large, then of course the numbers will come out also large, so, and that failure won't govern. Good question. Is it possible to determine the general strength of an anchor without requiring to input all the forces like in the previous versions? Yes, you can. Basically, if all your forces are 0, then the program actually doesn't really calculate anything. It skips because it just thinks that that force is simply not present. So what I would suggest, just put 1. Put any small value. 0.5 kips for tension and 0.5 kips for shear in X and 0.5 kips for shear in Y, whatever. Just put any value that will trigger the calculation of the strength. Is it a triangular or parabolic compressive block distribution for the tension compression forces? Is the base plate considered flexible or rigid in this analysis? Okay, the first thing is base plate is considered rigid. Yes, that is very important because that is the only way we could get to that plane section remaining plane assumption as close to that assumption as possible. If the base plate is flexible, then we are really far off. Is the compressive block? It is parabolic, as I said, that we consider, and that is why, if you remember on the program interface in the concrete parameters, we do have those 2 strain values. The one is epsilon 0, 1 or 0c, whatever. That signifies the strength at which the concrete is at its peak strength, peak stress, and then 0.003, which is the ultimate strain in concrete for unconfined concrete. And you could change those values if you want, but typically just leave them as they are. And based on those values and the strength of concrete, we determine the concrete stress strain curve. And that stress strain curve is used in that beam flexion analysis to determine the tension and compression. How is the overstrength factor considered internally in the software? There is an input box where you can set your overstrength factor. If you are using 31811, if you are using 31805 or 31808, then 2.5 is the only value that they allowed you to use, and so that is built into the program. So you cannot change it. If you are using 31811, then you can type, by default it is still 2.5, but you can change it if you want. And if you do set an overstrength factor, then the program will check for the ductility analysis to that is, if you require seismic the provisions to kick in, the ductility situation is checked. If your failure is ductile, is checked by considering the forces that you have calculated and considering the strength. First it will see that if the governing strength in tension, let's say, in tension is from the steel failure, and if it is, then it's fine. And of course, for steel failure governing strength, Appendix D has some more requirements that has nothing to do with the calculations, but there are certain detailing that you need to make sure that you have in the installation of the anchor, like you have to provide a sitting width, a sitting length for free stretching of the anchors, etc. But beyond that, as far as the Appendix D calculations are concerned, the program checks if the steel strength is the one that is governing for tension, if it doesn't, then it will check if then it will see that the other options that Appendix D gives you, like the maximum forces. So whatever the strength is, that is then compared against an imposed load that is scaled up by the overstrength factor. And there's another option too, where the governing strength is compared against the forces that could be transmitted to the anchors, possibly by there's a maximum force that could possibly be transmitted to the anchors by the attachment itself. Like if the base plate is failing under a certain load, then that is the load that is the maximum load that is going to be ever transmitted to the anchors, and so that's how it is done. Oh, I see. Yeah. So when using leveling nuts, you will not have distributed compression on the base plate. So beam analysis, yes, won't be exactly correct. That is true. And yeah, you could say that it is a limitation of the program, but yeah, I mean, but how much of an error it causes in the analysis, it's hard to say, because yeah, but I mean the nuts will compress against the base plate, and I'm guessing that under high loading the base plate will probably come in touch with the bear on the concrete surface, at least to a good extent. But it's a good point. Yes, no, we do not consider that. I don't know if there is any way to actually even consider that. I mean, there are situations in the field that cannot always be, replicated in the program. But this is a good point. I'll give it some thought if there is anything that we could do to incorporate these kind of situations in the program. Could you explain more about reinforcing the concrete to where concrete breakout modes are not considered? Well, that is really about Appendix D, and we do not, if I had more time, I probably could have gone into that. But quickly, I mean, you could provide anchor reinforcements that are crossing the potential failure planes of concrete breakout. So it could be potential failure planes of concrete breakout in tension, or it could be the potential failure planes in shear. And those anchor reinforcements, and those reinforcements should be, and there are very specific requirements in Appendix D about the layout and the dimensions and the distances, etc., of those anchor reinforcements, so that they could be considered anchor reinforcement. You cannot just provide anything and call it anchor reinforcement. So, but once you meet all those requirements, then you could just calculate. We could assume that the whole shear or tension, whichever it is, being transferred by the reinforcements directly, and the concrete breakout does not take place at all. And now something I want to mention in the beginning, that this seminar was not, as I said, not on Appendix D, but it was basically on the program. But if you think that a seminar on Appendix D would be helpful, then please let us know. There will be we will send you a evaluation form after the seminar. So please, there will be a place in that for you to mention any topic, seminar topic that you would like to see from us. So please mention that in that evaluation and form, and so we will see how quickly we can arrange for a web seminar. Of course, that will be a more full-fledged, maybe 2.5 hour web seminar, or even more than that, not a short presentation like this. in the future, is there a point to include Hilty, Simpson, and Redhead interface just in a click of a button? I don't know if we can include their interfaces. Can we include their anchors, like the whole anchor databases in our program? I don't know. It would definitely be very, very good to do that, of course. If tension or shear reinforcement is used, I'm assuming that is it. Anchor reinforcement I'm talking about. Do we have to input the total reinforcement in the box, or is it just the effective reinforcement per bolt? No, it's the total, and it's also not the reinforcement. It's the total design force of the reinforcement, which is 0.75 times the total cross-section area of the reinforcement times f sub y. That is the design strength of the anchor reinforcement, and you enter the total design strength in the relevant direction, like it could be the tension, or it could be for shear in the x direction, shear in the y direction, not per bolt. Are there various column sections available for input into the analysis? No, because that doesn't really come into the picture directly as far as Appendix D is concerned. I mean, we just show a wide flange section just to show you where the member is attached. So if there is any eccentricity in the member location, that will be reflected. But other than that, no. Okay, so now I see, never mind, when using leveling nuts, you would likely have grout between the base plate and the concrete. So distributed compression would still be present. That's a good point. Yes, I did not think of this before. Yes. And the beam analysis could work to determine the tension in anchors. Yes, good. Thank you for pointing this out. Yes. Does the output of the program indicate if applied loads are okay, or just give maximum T and V capacities? No, it does indicate. You will see the, if the applied loads are greater than or equal to or less than the governing failure modes, and then you'll have the interaction equation mentioned. So if the interaction equation is good or bad, like if it is within that 1.2 limit or exceeding that. No, a program does give you everything. Can you please explain how to interpret the software results for brittle failure using the overstrength factor? Well, the brittle failure, comes into the picture only when you need to apply the special seismic requirements of Appendix D. And so what the program does, if when required, the program will check the various options of the brittle failure, various options for checking this brittle failure that are given in the code, and it just lists all those options. Like option 1 is the steel strength, is the governing failure is from the steel failure. Is it if yes, then yes, then you're good as far as option 1 is concerned. Then option 2 is the strength, the governing strength in a particular direction. It could be strength, tension, or shear in X and shear in Y. If the governing strength is less than the maximum tension, let's say in this case, if you consider tension, see, the governing tension strength is less than the maximum tension that could ever be imparted to the anchors at a point where the attachment, like in this case the base plate, fails. So you need to calculate what would be the tension that will come on the anchor when at a force level when the base plate actually yields. Or actually, if the base plate is an yielding material, then you also have to consider the strain hardening and overstrength in the base plate material. So you need to enter these values, that the maximum tension that can ever be imparted to the anchors at a time where the attachment fails. and that value you need to calculate yourself and need to enter in the program. And then comes the overstrength, the third option, where if the program will check if the strength in tension is less than the imposed loads, and in this case the imposed loads are the actual loads that you already entered, like tension that you entered on, or the moments, the net tension coming from the moment. So when you scale up those imposed loads by the overstrength factor, is the strength in tension less than that scaled up forces? So we have three options for tension. We have two options for shear. You need to meet at least one of these. If you meet at least one, you're good, and the program will say that okay, you're okay. So it will consider each of those options and see, okay, option 1 okay, option 2 not okay, option 3 not okay, but option 1 was okay, so your design is good. But if all three options are not okay, then you have to revise your design, you have to do something about it. So I think that's pretty much of it. I do not see any more questions. It was a wonderful experience, presenting in front of such a large crowd and lots of good questions. Thank you very much. And I will end the seminar at this point. So thanks again, and have a wonderful rest of the day. Thank you.